Welcome to the very last example you are going to do on the light board for this course, and thank you for bearing with me through 130 of them. In this exercise, we have the function g of s, and you're given the Nyquist plot for the function g of s. The question is simple. Given this Nyquist plot, what is the range of k that makes the system stable or unstable? This Nyquist plot was obtained for k equals to 1, and as we can see here, we have no unstable open loop poles, so p equals to 0, and for k equals to 1, there are no encirclements of -1, so the system is said to be closed loop stable. However, as we increase k, this point on the real axis, on the negative real axis, will shift to the left, and eventually will touch -1 and eventually encircle -1, which will result in 2 encirclements of -1 and 2 unstable closed loop poles. So what is this maximum value of k? To determine the maximum value of k, we need to determine where exactly we are crossing the negative real axis. And how we do that? Well, we need the magnitude of the transfer function when the phase is -180 degrees. That is precisely the point where we cross the negative real axis. So let's do that. We can start by writing the transfer function as a function of j omega. This is 100 over j omega plus 1 squared, j omega plus 10 squared. And you can now expand this. This is very simple math. And as we expand this function, we are also looking for the real and imaginary components of the denominator. And after some straightforward manipulation, this is the result. Here we can see the real components of the denominator, and here we have the imaginary components of the denominator. The reason for splitting this way is that we are only looking for the imaginary part of the transfer function, because we know that when the phase is -180 degrees, the Nyquist plot is crossing the negative real axis, and the imaginary part of the transfer function is 0. So to find now the imaginary part of the transfer function, we need to get rid of this denominator that has a complex number. We can multiply the numerator and the denominator by the complex conjugate of the denominator, that is omega to the power of 3 minus all that. And here we have the transfer function multiplied by the complex conjugate of the denominator. You notice the negative sign change as opposed to positive. We can now clearly see that if this element here is called A, so is this one. If this element is called B, this entire element here is called -b. When you multiply these two functions, the denominator becomes a squared minus b squared, and b squared has a j inside it, so when you do j squared, that is -1, the complex part disappears from the denominator. It will make its way to the numerator. I forgot to add a j here, so this is multiplied by j, of course, as the same as the denominator. So now from the numerator, we can take the real part and the imaginary part of the transfer function. The real part will be 100 times this portion divided by a squared minus b squared. And the complex part is 100 times this divided by the same thing. We can now write the imaginary part as -100 times 220 omega minus 22 omega to the power of 3 divided by a squared minus b squared. And this is equal to 0. We want to find the values of omega that make the imaginary part 0. We know that when the imaginary part is 0, we are sitting on the negative real axis, and the phase of the transfer function is -180 degrees. Solving for this is very simple. We are left with what is inside this parenthesis. We have 220 omega minus that. 3 possible solutions. Omega equals to 0. This is not a valid frequency. And omega equals to plus minus a square root of 220 divided by 22. The square root of 10 is around 3.16 radians per second. Now we know the frequency that it makes the imaginary part 0, therefore we know the frequency that it makes the phase of the transfer function 180 degrees. We can now evaluate the magnitude of the transfer function. By evaluating the magnitude of the transfer function, we are determining how far we are from 0 on the Nyquist plot. That is the point we are trying to evaluate now. So let's do it here. The magnitude of this transfer function, magnitude of j omega, is very simple, is 100 times k, well, because k is coming from here, divided by the square root of omega squared plus 1 all squared times omega square root of omega squared plus 10 squared all squared. And you can now evaluate this at plus 3.16 radians per second. This gives a magnitude of approximately 0.08 K. Now let's bring back our Nyquist plot here, and now we know that we are sitting at 0.08 K. For closed loop stability, we need this point that crosses the negative real axis to be to the right of -1, because here we have no unstable open loop poles, P equals to 0. If the Nyquist plot is to the right of -1, then N equals to 0 and Z equals to 0. No unstable closed loop poles. However, if that point is exactly at -1, then the system becomes marginally stable. And if we are now to the left of -1, then the system becomes closed loop stable with two encirclements of -1, Z equals to 2, two unstable closed loop poles. How do we make that point move towards -1? Well, we want this value to be 1. We want the magnitude, the distance from the origin to be 1. So we have 0.08 K equals to 1. K equals to 1 over 0.08. And this is approximately 12. I cropped some numbers here, but this should be around 12. Now notice that when K equals to 12, this becomes 1. So the Nyquist plot shifts towards -1, and the system is now closed loop. The system is now marginally stable. Anything greater than 12 makes the system unstable. Now let's bring up the Bode plot for K equals to 1. Based on the analysis that we did here, what is the gain margin on the Bode plot? The gain margin is a positive number, of course, because you have to increase the gain to make the system closed loop unstable. But what is it? Where is the gain margin here? To make the system closed loop unstable or marginally stable, we'll need now to shift the entire Bode plot up to reach 0 decibels at 180 degrees of phase. And by how much do we need to shift the Bode plot up? Well, by 20 log of 0.08, which is around 21.7. And by shifting it by 21.7 dB, then we reach now the critical point, the system becomes closed loop unstable. As a function of K, we could have written this times K here. In fact, the 20 log of 0.08 is negative 21.7 dB, and this would be plus then 20 log of K. When this becomes 0, if you want this to be 0, what is the value of K? 12. And then this becomes 0, the Bode plot shifts upwards, touches 0 dB, exactly when the phase is negative 180 degrees. The system is marginally stable, past that becomes closed loop unstable. Here is the root locus. Looking at the root locus, what can we say? We can clearly observe the same thing. For low values of K, the system has no unstable closed loop poles. Past a given value, the system has two unstable closed loop poles, and what is that maximum value is exactly 12. We can verify that using the Routh Hurwitz. Let's do that. Okay, now let's verify our results using the Routh Hurwitz. What is the characteristic equation of the closed loop transfer function? There is 1 plus K times G, and if you rearrange that, this becomes S plus 1 squared times S plus 10 squared plus 100K equals to 0. We don't need to expand these two terms here, I'll just give you the result, and here it is. Now that we have the polynomial, we can do the Routh array, starting at s to the power of 4, and going all the way to s to the power of 0. What are the coefficients? We have for S4, 1, for S3, 22, S2 is 141, S1, 220, S0, 100 plus 100K, and this element is 0. We can look at this element here. This is this multiplication, 1 times 220 minus 141 times 22 divided by negative 22. This is 131. This element, because this cell is 0, is 100 plus 100K. This cell is 0, because this cell is 0, this one is 100 plus 100K. And this one here, we're going to call that A. A is 22 times 100 plus 100k minus 220 times 131 divided by 131. We can now solve for k here. We can equate this to 0. So for k is 220 times 131 divided by 22 minus 100, all divided by 100. And guess what? K equals to 12. So what happens here? When k equals to 12, we have a row of zeros, marginally stable. When k is smaller than 12, all positive values, no sign change, system is closed loop stable. When k is greater than 12, then A becomes negative. We have no sign change, no sign change, one sign change, two sign changes. Two sign changes, two unstable closed loop poles, as you could see from the Nyquist and from the Routh locus plots. So the analysis is consistent, everything tells the same story. And this is the very last example we are solving together using the light board for this control systems class. I do hope you enjoyed this setup. I'll see you next time. Bye.